Welcome. In this lecture, we are going to focus our attention on foundational aspects associated with pipelining. And so what exactly is pipelining? Well, we want to start off with a brief definition in that pipelining essentially relates to uh, the ability of instructions to be executed in a manner that is concurrent. And so we want to try to see how we can maximize performance efficiency by having instructions executed in a sequential, in a manner that allows for concurrent aspects to occur. So in order to consider this, let's kind of think about some other aspects. We've talked about latency and throughput, where we consider that latency is going to relate to the cycles per instruction, where we're considering each instruction takes a certain amount of time to complete or to execute. So let's also consider the amount of time between when the instruction is issued and when it's complete. And then with throughput, we're considering the, the instructions that complete in a given span of time. And so considering throughput, we want to leverage how we can reduce the cycle time for the length of our longest instructions in stage. And this leads us to understanding how we can design a processor that can exploit the ability of instructions to be pipelined. And so let's kind of consider a simple scenario. And in this scenario, we're going to call it Bill's Sandwich Shop. Bill is a small town guy who started his sandwich shop, and he has a very good business going. And he started out as a one-man sandwich shop owner, but now he's trying to build up his business and improve. And so now, instead of Bill just making all of the sandwiches in the shop himself, he has a team of employees that are working with him and that are helping him. And so let's consider Bill has 5 employees, and each employee has their own station that they're focusing on. One employee will place orders. The next employee selects the bread. The next employee selects the cheese, and the next employee selects the meat. And then the last step is that the veggies are selected. So as a customer places an order, they will incrementally progress down the chain, adding each component that they need to their sandwich. So this makes sense. And so now what we have is we can introduce the ability for multiple orders to be placed within the sandwich shop. So let's say we have an employee. To ensure that an employee isn't idle or twiddling their thumbs, as each sandwiches passes through the station, another sandwich will come down the aisle. And so if we consider this approach, we can see that by the time a 5th order is placed, the first order is being finished up, and then the second order will be finished up, and then the third order will be finished up, and then the fourth order will be finished up. So this means that most of the time during peak busy periods, during busy lunches, sandwiches can roll out in a very quick and efficient manner, where each employee has work that is being done successively. And so how would this relate to us in terms of understanding the appropriate instructions? So let's consider that each station or each order being placed relates to our finite state machine, where we have fetch, decode, and execute being our micro states in our data path. Well, we know that sometimes that some of these micro states are not going to be utilized all of the time. So instruction 1 will be passed through to fetch and then to decode. And a lot of times the majority of the work will occur in our execute stage. So we'll have our instruction in through fetch and then our instruction out after executing. And so representing this even with our pipeline analogy, we see this as kind of like a waterfall model, in that for fetch, decode, execute occurs for one instruction, and then for the next instruction, and then so forth successively. So this could be represented as, by the time instruction 1 is executing, instruction 2 is at decode, and instruction 3 is entering the fetch stage. And so if we're able to overlap execution in this way, then we can provide for an easier or a more efficient approach to executing multiple instructions successively over time. So this provides us for the execution occurring in 5 cycles for completion for the 4th instruction, versus previously it occurring in 9 cycles. So that is the benefit of pipelining, in that we want to be able to represent these instructions in a more efficient, to execute these instructions in a more efficient manner. And so what will we need in our data path in order to make this a reality? And so we know that for our data path is going to consist of fetch, decode, and execute. And execute could have various operations that are involved, right? So let's go back to our data path circuit design, where we have our program counter, we have our ALU that can take input from our A and B registers. We have our memory address register, we have our instruction registers, and we have memory as well. And we have control logical units to represent various different instructions that we can utilize. And so for each microstates, what exactly do we need? What units in our circuit are we gonna need to use? So for the fetch microstate, we know that we're going to need to make use of our instruction register, our ALU, our program counter, as well as memory. For decode, we'll just need to make use of our instruction register. For execute, when we're considering an add, we're going to make use of our instruction register, our ALU, and our register file. For considering execute, where we're loading, we'll make use of everything required for our execute add, but also need to make use of memory as well as a sign extender. And so what are some observations that we can make in considering this? Well, we can consider that we notice that for each of these steps that our instruction register is going to be used in every one of our macro states. And we know that each state is also going to need to do a different amount of work, which we can see in execute. It could have, it's going to require different work as well. So we also want to consider with the register file that only the writing is exclusive. So we can do the reading simultaneously. So what are some points that we want to consider when we go back to our comparison with Bill's Sandwich Shop? We know that work is done by each station is roughly equal. So every sandwich goes through every station, regardless of what you want or you don't want. So this is a point to note because not everyone will want cheese or meat or veggies. Some might just want meat, some might want cheese only, some might want veggies, cheese, and meat. But what is always required? The order form is passed from one station to the next. So each station is basically going to need that order form in order for it to do its part and process each component required for assembly. And so how exactly can we mimic the work for the sandwich assembly scenario? With the fetch, decode, and execute, we here have an unequal division of labor. So this is going to kind of be a violation in that we know that a lot of time execute is going to take the most time. So if Bill were to try to mimic this, it could result in problems in that if he were to cut back on employees, this might result in increased waiting times because you'll have only 2 workers who only work about a third of the time. And so to avoid this, you do want to have 5 workers with the distribution of work. So what can we do in order to mimic this equal distribution? So let's take a look in what we might need to modify with regards to our macro states. What needs to happen for every instruction? That's a foundational question to consider. Okay, so we know we need to fetch into our instruction register and increment the program counter. We're going to need to read registered contents. We're going to perform arithmetic and logic appropriately, possibly. We'll need to perform address computation. We'll fetch and store the memory operands. And we'll write to register as well. So in this case, it looks like we have extended it into 6 steps that we need, but in actuality, we can combine these processes together. And this gives us our 5-step approach. So this way, we're providing for a more equal amount of work or work distribution. And so what might be needed for us to read registers without decoding the instruction? So what exactly does the bread guy care about? The bread guy is going to be the first active step in the process. And before he can do anything, what does he need to take a look at? Well, he will need to look at the order form. And so when we consider our instruction pipeline, what is going to be the equivalent of the order form? And so that is going to be our instruction register. And so this is where the symmetry of instruction format comes into play and can have an effect on the way that our data path can execute. So this can vary based on the instruction set, the way the instruction set is implemented and utilized. So let's consider the steps that every instruction will need to go through. Some stages don't need to do anything for some instructions. We have our instruction in, and it will be processed. It'll fetch into the instruction register and increments the program counter. And then we'll have to do our read register for the contents. We'll perform our execution operations. We'll either fetch or store to memory, and then we'll write to the register possibly. So each stage is going to work differently. And so why exactly does Bill use 5 stages rather than 3 in his sandwich pipeline? Is it because he copied the instruction pipeline? He only could find 5 workers. He's solving the unemployment problem. He wants to make sure that the amount of work done by each station is roughly the same. He's a nice guy. Or are you getting hungry? Well, of course, we can go with D. He wants to make sure that the amount of work done by each station is going to be roughly the same. And so what might be further needed for us to realize that, or how can we electrically isolate each stage? So if we think about our sandwich assembly line, each stage is going to pass 2 things to the next, the order form and a partially assembled sandwich. And so in our data path, how would we represent those components? We would have to use the instruction register would be equivalent to the order form. And so what exactly would represent our partially assembled data sandwich? Well, where are we pulling things from? We're going to need to pull things from the register. And so we want to use the registers to act as a wall to isolate the actions of each combinational logic cloud that we're going through. And so once each stage is working on a different instruction. And so once the stage has completed its function, it has to place the results of its function back onto our place for storing and checking until the next clock cycle. And so this introduces the need for registers to send their output to drive the next stage in regards to computation. And so what can we do in order to separate our pipeline boxes? Really, the boxes are just combinational logic clouds. So we already know how to separate them. And so in this aspect, we're going to use a special register called a pipeline buffer. And the buffer is going to represent the output stage after each combinational logic. And so buffering allows for us to keep the independence of each stage. And a pipeline register is what we refer to when we're talking about buffering between the various stages. And so using the buffers, we're able to pass some of the clock data that is needed. In our next lesson, we'll go into detail on some of the combinational logic and circuitry needed to exploit and explore our new data path, as well as appropriate register components that will be required as well.